All right, so today I'm going to give you an introduction to quantum computing concepts from more of an intuitive perspective, and we'll also go through the syntax for how to write out quantum state, and we'll get through one simple algorithm. All right, so one thing that's important about quantum computing is the distinction between bits and qubits. So in a bit, we know we have a single piece of information that has either a 0 or a 1 stored in it at any given time. A qubit, on the other hand, has more complex state, including both 0 and 1, with a probability of measuring a 0 or a 1 when it's read out. Okay, and so this has interesting questions that get raised by this, because then it's a little bit like looking at it from the perspective of a data type. Okay, so if we have any piece of data, we always ask what values it can hold and what operations we can perform on it. But in quantum computing, this actually is interesting because we have some added questions that get raised, which is what values can we read? Because in quantum, the values that it can hold are more complex than the values we can read. And that's a distinction we don't have in classical computing. Right? And then because it's so different, then we have the added question of, well, what algorithms can we write? How do we use these operations to make something that's potentially useful? Okay. All right, so today I'm going to go over some basic quantum principles and the implications towards quantum computing for them. So we'll go through superposition, state and operations, measurement, entanglement, and reversibility. And then we'll go through one quantum algorithm. All right, so the text is too small for you to read, but in this diagram, in this comic, it says there can be no peace until they renounce their rabbit god and accept our duck god. And you might notice that the flags are identical. Right, so the whole point of this joke is that the same picture can be interpreted as both a rabbit and a duck. All right, so that is one of the basic concepts of superposition, is that something that you see can actually hold two different things at once. So we have, I don't know if you remember the viral dress. Is it blue and gold? Is it blue? Is it gold? It depends on who's looking at it and the lighting. Okay, there was also a viral post about a recording that some people heard as Yanni and some people heard as Laurel, and we're going to explore that in a minute. And we have lots of optical illusions. So there are lots of things that we find interesting as humans that are presented one way and can be interpreted two ways. Okay, this isn't enough to be useful for quantum computing, but it's a step in the right direction. All right, so if we actually explore this Yanni-Laurel clip more, we can see that it's not just those optical illusions, it's not just that they're holding two things at once. It's about what you perceive when it's measured. And so if we listen to it, at one extreme, okay, then we can hear Yanni. If we do it at the other extreme,
Laurel.
then we can hear Laurel, but if it's somewhere in between, a little more, So we can see that as we get gradually over there, some people are going to hear Yanni, and some people are going to hear Laurel. And that's the measurement. And even more than that, you could set it up, you could move the slider to a certain position so that you could control the probability that someone would hear Yanni versus Laurel. And that's when we start getting into something that's more like quantum computing. It's this ability to not only have something that is two things at once, but also our ability to manipulate it and control that probability of reading out 1 or 0, or Yanni or Laurel in this case. Okay, so go back to the slides. Okay. The other thing about quantum computing is that 0 or 1, that's just the measurement. That's not the complexity of a state. So so you've seen these t-shirts probably that have these different emotions on them, and then you have different facial expressions. Now, if any of you are parents or have experience with small children, you'll notice that for small children, or like infants, you might have the same expression for hungry, anxious, bored, tired, sad, and upset. And then you have another expression for perhaps happy, proud, and excited. So a baby, an infant, is very much like quantum state in that the actual state of the baby might be quite complex, but we have no way of reading that complexity of state. And that complexity of state affects the operations, but it's not something that we can read out. Okay? So there's some relationship between the state that's held and the state that we can read. Okay, so let's get into a little bit of notation so that when we get into the math, we can understand what's going on. So this is called Ket Notation. And on one level, it expresses the probability of reading a 0 or a 1. So whatever is in the Ket there is a 0 or 1. That's what we're reading out. And then the variable before it, if you square that variable and take the absolute value, that's the probability of reading out that value. So in this case, the absolute value of a squared is going to be the probability of reading 0, and the absolute value of b squared is the probability of reading out 1. And because there are only two states, 0 and 1, if you add up those probabilities, it always has to equal 1. There is more complexity to the state, like I said. So there can be a negative sign there, and there can be an imaginary I there. So those refer to aspects of the phase, the complex state, that we're not able to read out at the same time as we're reading out the value 0 or 1. All right. So there are also shortcuts that we take, just like we do in algebra. So in algebra, if I have 2x, then, or 1x, 1 times x, I don't have the 1, I just say x. Also, if I have a term that is a 0, 0 times it, then I drop that term. So we have a lot of simplification. So if we have a term that's 100% probability of reading out a 0 and 0% probability of reading out of 1, then we just express the 0 and we drop the 1 that's in front of it. It is also true that if you have the same component in front of all of your numbers, then you can factor that out. Okay? So if you see that there's a 0 and a 1 here, that doesn't mean 100% probability of reading a 0 and 100% probability of reading a 1. That just means equal probability of reading a 0 versus a 1. We also have a matrix notation, which is important because we use matrix multiplication to do gate operations. So I take the terms in front of the 0 and the 1. The top one refers to the probability of reading out 0, and the bottom is the 1. So we just transfer those and put them in matrix notation. All right, so the way that operations occur, the way we calculate them is matrix multiplication. So first, I'll show you the X gate, which we refer to as the bit flip gate. This flips the probability between 0 and 1. And so the gate is expressed as a matrix. And the way you calculate it is, let's say I have a qubit right now that's in the state alpha 0 plus beta 1. And so I put that in matrix notation, alpha on the top and beta on the bottom. And if I calculate this out with matrix multiplication, I'll find that I get beta over alpha, which means beta is now the term for the 0 and alpha is now the term for the 1. Okay. Z is we refer to as the phase flip gate. And so again, we can do the matrix multiplication here, and we'll see that changes the sign of the second term. All right, so the Hadamard gate is interesting because this is the one that causes superposition. So we can take a value that's, I'll show that in a second. But anyway, it adds the A alpha plus beta divided by root 2 for the 0, and then it subtracts it for the 1. So why don't we see what happens when I start with something that's entirely 0, So if I start with something that's 100% probability of being a 0, I end up with a 50-50 probability of being 0 or 1. If I start with something that's 100% probability of reading out a 1, I end up again with something that has a 50-50 probability of 0 or 1, but notice that the phase is different. This difference in the phase is going to be important when we get to our first algorithm, Bernstein-Bazarani. Okay, so now we have learned two sets of information. We've learned about superposition and state and operations, and so we'll move on to measurement. All right, so measurement, we're used to, in the classical world, measurement not perturbing state. So if you are driving your car and a radar is detecting your speed, that radar does not affect the speed. Okay? Likewise, when we watch the Olympics and we see the swimming trials, the video is showing it and it superimposes on the swimmer, but it doesn't affect the swimmer. It doesn't make the swimmer more tired. It doesn't stop the swimmer from swimming. Okay. However, there are other things in daily life where the measurement does affect state, right? Why do we wear the bib at the dentist's office for the x-rays? Because the x-rays are actually dangerous to our body. So the measurement apparatus affects our state as a human. And if we hold our breath twice in a row, then we may not be able to hold it as long the second time. So the way we measure data, something affects that measurement in itself, the state of the thing we're measuring. Okay. All right, so for quantum computing, if I have a superposition, it doesn't have to be 50-50, but whatever it is, when we measure the state, that collapses the superposition. And unless we do other operations, then if we read out a 0, we will always read out a 0 after that point. And if we read out a 1, then we will always read out that 1. It's a good thing that that's not the case for children, because if I were to peek in on my daughter and she was screaming, I would not want that to be the state for the rest of her life. Okay? All right, go ahead. All right, so this has an interesting corollary, the fact that you can't measure, is that it turns out that then you can't clone state. So we can make qubits. If we know what state we want in a qubit, we can do the same operations to many qubits and get all of those qubits in the same state. But if I don't know the state of a qubit, and I want to copy that state, that's something that we can't do. Okay. All right. Okay, so now that we know more about measurement, let's go through entanglement. So entanglement is what gives us the real power in quantum computing. So let's look at these boxes. And are these boxes pointing down to the left, or are they pointing up to the right? Okay. Well, could be either one. So it could be that when you look at them, they look up to the right, or it could be that they look down to the left. But it turns out that it is really, really hard to get it so that you can see one down to the left, one up to the right, and the other one down to the left. Your eyes, your mind entangles those three. If you try really hard, like I can maybe get it for a fraction of a second, and then my brain makes it all go the same way again. Okay, so that's one form of entanglement, but not the way it works in quantum computing. So normally, if you do two coin flips, they're independent. So if we look at the 4 possible outcomes of those coin flips, we know that there's a 25% probability of getting any 4 of those combinations. Okay? With entanglement, it turns out that you could set up a scenario so that it's guaranteed that both of them are heads, or both of them are tails. You don't know which one it's going to be. There's still a 50-50 probability of each coin having heads or tails, but the states are entangled such that they're both heads or both tails. You could also entangle them such that they're always different, so that no matter if one is a heads, then the other one is a tails. Okay? So let's look at how that works with quantum computing. Okay? So in quantum computing, this would refer each coin would be a qubit. And so if we do a coin flip, that's a 50-50 probability of each direction. So we have the following state. Okay? So when we're expressing the outcome of 2 qubits as opposed to a single qubit, If they're independent, then we take, then now we have the states 0, 0, 0, 1, 1, 0, 1, 1. So we take the terms in front of the appropriate ones and multiply them. And you can see that if we have a 50-50 probability for each one, we're going to have a 25% probability calculated out. Okay? All right. So we're going to end up with this state if they are unentangled. Okay? All right. So let's look at what we would end up with if they were entangled. So if I'm claiming that we can get to a state where both are heads or both are tails, then this would be the end state, right? We have a 50% probability of getting both heads, and then we have a 50% probability of getting both tails, and then zeros in between. Okay? All right, so let's see how we would get that. So there's something called a C-naught gate, which I'll refer to as the entanglement gate. Okay? And so what the C-naught gate does is it has two inputs, and the C-naught gate itself is this matrix. And the way it's typically explained, one of the bits decides whether or not to flip the second bit. So if I have a 0 coming in as one bit, then the A and B from the second bits, as we saw from how you take two independent bits and make them 2-bit combinations, we would get A, B, 0, 0. And we can see from this matrix that that would not affect it. But if, on the other hand, I had a 100% probability of 1 coming in, that would end up with the A and B in these terms, because now we have 0, 1, and 1, 1, as opposed, I'm sorry, this is 0, 1, 0, 0, and 0, 1. This is 1, 0, and 1, 1. So we would end up with the A and B on the 1, 0, and 1, 1, and this matrix would flip those. Okay. So if we have, so now we have a circuit. So as was explained previously, circuits, unlike hardware circuits where they refer to something physical, where these are wires and it all exists at once, in quantum this is a diagram where the left side is the inputs, and then time goes to the right, and those are operations occurring on the qubits. Those are not, there's no physical gate sitting there that electricity goes through. So these are operations that are occurring on those particular qubits. So if I start out with two qubits that are 100% probability of being 0, and then I put one of them through a Hadamard gate, which makes it a 50-50 probability now of being a 0 or a 1. And then at the conclusion of that, if I look at the state of these two, I will have right here, so I will have a 50% probability of 0, 0, and a 50% probability of 1, 0. Okay? Now, if I put that through the C-naught gate, then that will flip the probabilities on the second two, just like what the C-naught does. And what I will end up with is a 50% probability of 0, 0, and a 50% probability of 1, 1, which corresponds to the coin flip, where now I'm guaranteed that if I measure one qubit, the other qubit will have the same value. Entanglement does not always mean that the two qubits have the same value. That's just the entanglement that I illustrated here. But in this case, what I've guaranteed is that those two qubits, if I measure one, even though that one has a 50% probability of being a 0 or a 1, if I then later measure the second one, it will have the same outcome as that first one did. All right, so this is important for quantum computing because, for example, let's say I have a 4-qubit value, and I want to constrain it so that it's always divisible by 3. Now, if I look at the individual bits of those, we can see that they have, the individual bits each have a 50% probability of being a 0 or a 1. So without entanglement, I would not be able to constrain them so that they're always divisible by 3. But with entanglement, I can make it so that I only allow these combinations of those numbers, and now I've limited it so that it is only divisible by 3. Okay, so now we're going to do the last quantum principle, reversibility. All right, so reversibility, there are lots of things in daily life that are reversible. I can zip and then unzip my clothing. We can freeze ice and then melt it and then refreeze it. There are also lots of things that are not reversible, right? I can't untoast bread. I don't know if ringing a bell, letting the cat out of the bag, right? There are just things that you can't reverse. All right. Okay. So let's talk about an operation. So let's say that I want to reverse the commute that I did to get here to the convention center. What information would I need, or how could I reverse that operation? I want to get home again, or I want to get back to my hotel room. The key is that I can't just do that. I need more information. So what information might I need in order to get back? Well, maybe I need my starting location. Okay? Well, is the starting location enough if I don't know how to get there? Maybe I need a map. But then, even if I have the map, I have to figure out how to get back, and maybe the way I get back won't have been the same way that I got here. So maybe if I had the sequence of left and right turns and how many steps I walked, that would get me back. And then I wouldn't even need the starting location, right? That would be a lot closer to computation, where you know the sequence of operations to get you back to that value, but you don't know what the starting value was. Okay? And are we going to go to the level of saying I have to, retrace my footsteps in the exact location? No. I mean, what we care about in quantum is that we get back to the exact starting location. So let's look at something closer, which would be mathematical operations. So if I were to look at incrementing, so if I knew that I had incremented a number 10 times, I could reverse that, because I can just decrement that number 10 times. Okay? But what about multiplying by 7 times 3? So I would know that my outcome was 21, and I know that I did a multiplication, right? If I know the outcome and the operation. That's pretty reversible, except that I don't know which of the inputs was 7 and which of the inputs was 3. Okay? And then if I know that I divided 48 by 3, or let's say I know that I got 16 as my result, and I did a division. That is not enough information for me to reverse that, because I don't know that I just need to multiply by 3. There are lots of different divisions that could result in 16. Okay? Now, quantum computing has a hard requirement that every operation has to be reversible. So if you only know the operation and the result, that's not enough information to allow you to reverse it. And so, So in classical computing, we may have a division unit where I have an input x and y, and maybe I have outputs that's the result of the division and the result of the and the remainder. Okay? But for quantum computing, that's not sufficient, because we have this requirement of reversibility. So in quantum computing, we have extra input. We have an extra output, which in this case is going to be one of the inputs, because that would give us the information we need to reverse it. And we need an equal number of inputs and outputs. So in quantum computing, we have what are called ancilla bits. Ancilla bits are not part of the useful computation, but they are part of the required computation, because they contain the extra information necessary to reverse computation. Okay, so this is the reason why when, for example, for this C0 operation, it seems like after I do it, I wouldn't need the input bit 1 at the end, right? It seems like I should just be able to take those two and have the output be B of 0 plus A of 1. But because we have to be able to reverse it, we need that first input still, and that will be our end syllabate if we don't need it for anything else. Okay. Okay, so you might have seen recently that there was a headline that scientists reverse time with quantum computers in breakthrough study. They did not at all reverse time. All they did was get higher reliability on their reversibility than others had before them. So you should be careful of the headlines with quantum computing. I don't know, it just seems like the headlines for quantum computing seem to be much more spacey and, you know, trying to claim impossible things. And so also, newsflash spoiler alert, quantum teleportation is also not like Star Trek. All right, so we're done with the intro to quantum principles, and now I'll go through one of the first quantum algorithms. All right, so the purpose of showing this algorithm is to show that the class of algorithms, one class of algorithms for quantum computing is very different from what we use for classical computing. Okay? And algorithm development with quantum computing started with oracles, and I'll go over what oracles are in a minute. But these were used to develop an understanding of how gates can be used to perform computation. And so we'll learn one of the early ones today. And it in itself is not that exciting. I'm just showing it to show how quantum gates can be used to do computation. But they are a stepping stone on the way to Shor's algorithm. So this sequence of developing multiple algorithms helped theorists and algorithm designers understand how to play with gates to do something useful, eventually ending up with Shor's algorithm. Okay. So what is an oracle-based algorithm? Well, there are lots of oracle games that children play. So if I say, I'm thinking of a number between 0 and 100, that makes me the oracle. And then you give me a guess, 75. We know that's not the best guess, but, and then I say higher or lower, okay? So that's an oracle because I have the answer, and we have a protocol for how you ask me questions. You always ask me questions in the same format, which is a guess. And I always give you an answer, higher, lower, or correct. So that's the oracle. So there are lots of different games. Mastermind is an oracle-based game. The hotter, colder game to search for something. And then 20 questions. So there are lots of oracle games that people play. Okay? And so they have the characteristics that the oracle knows the answer, the guesser asks a question of a specific format, and the goal is to guess the answer in as few questions as possible. All right, so we're going to do Bernstein-Vazirani, and the purpose, this algorithm takes advantage of two important quantum attributes. One is that operations have to be reversible. So we're going to end up having a lot more information than we would necessarily have in classical computing. And we're going to exploit that. And also that the XOR can actually affect the control bit. So in the examples I showed for the C0 already, the control bit stayed the same, and it only affected the second bit. But we'll see how you can actually control, can alter the control bit itself. Okay. All right, so let's imagine that there's a secret bit string that has n bits in it. And that's what the oracle knows. And so I want an algorithm as the guesser to try to figure out what that secret string is. And the guesser has decided it's only going to give me, so I'm allowed to input a bit string, and every bit is a 0 or 1. And all it's going to give me is an XOR of the product of the two corresponding bits. So the 0th bit multiplied together, XORed with the next bit multiplied together, XORed with the next bit. And so if I'm on a classical algorithm and I think about how to use this, there's no tricky way to get around it. Really the only way that I can use it is to go through and with a separate query figure out what each bit is. So what I'm going to give it for each query is all zeros except the one bit that I'm trying to figure out. And then it's going to multiply all of these by the bit string, and so it's going to get zeros for all of these except the one that I'm asking about. And then that is going, the product of 1 times whatever that bit is going to be the same as the bit was. And then when I XOR that, I'll also get that bit out. So each time I query it, I'm going to figure out 1 bit. And so I have to query it n times to get out the result. Okay. All right, so if I were to try to construct a similar oracle in quantum, then I would start out, I would have my guess, which is these n bits of zeros or ones. And then I would use these C naughts to get out my result. But because it's required to be reversible, I have to go ahead and pipe all those results out. So go ahead and advance. So because it has to be reversible, I'm going to have to give it a bit to put the answer in. So I'm going to supply it a bit for the answer. And then all of those input bits are also going to come out as well. So what I can do is I do my C naught. And so, so the C naught you connect these connections are hard-coded, so they end up doing what would have been like the multiplication and the C naught, and then we calculate the output. So if the secret string is 0, 1, 0, 1, then in the 2 places where it's a 1, I connect the C naught. Okay? Do the next one. And then if the secret string is all 1s, then I'm going to connect all of them. Okay? Let's see what this does in the quantum operation. And so in order to understand why this works, we first have to understand something called phase kickback. So if I start a 0 or a 1 and put them through a Hadamard gate, we remember that that results in a 50-50 probability of each one, but the phase is different for each one. Okay? So the top qubit will result in 0 plus 1, and the bottom qubit will result in 0 minus 1. Okay? All right. So now if I do a C naught between those, so if I do a C naught between something that's not 100% probability of being 0 or 100% probability of being 1, but a 50-50 probability, the neat thing is that it actually flips the negative sign and tosses the negative sign to the 1, 0 instead of the 1, because a C naught flips the state of the last 2, right? So it flipped the state of the last 2. And so then if I figure out what those individual bits are, if I extract them back out from the 2-bit notation to the 1-bit notation, then I'll see that my top qubit now has a minus sign as well. And so what I did was, by doing this, there was no change to the second bit. The bottom qubit is still 0 minus 1, but I changed the top bit. Okay, so that's one cool thing. Now, the other interesting part is that a Hadamard gate, if you take an input and do a Hadamard gate twice on a 0 or twice on a 1, you get back the original one. So if I take the 1 and do 2 Hadamard gates in a row, I get back out a 1. If I put a 0 in and I essentially take this negative sign that was here and replicate it here, then now I'm going to get a 1 out. So by using this phase kickback, I was able to turn the 0 into a 1. Okay. All right, so then go back. So what that means is that wherever I'm connecting a C naught, if I input all zeros, then the last one, I flip to a 1 before I put it through the Hadamard gate. Then everywhere I connect that C naught, it's going to transform it to a 1 on the way out. So now I have an oracle that can take an input and output the secret string. And so this is a way that shows how you can use quantum gates to actually affect computation in a way to do something useful. Okay. All right. So then we can measure the results, and we'll get the secret bit string. All right, so that's the end of the introduction. We're going to have a break now to finish up any software installation. Those of you who are having